In this video, we will look at the three-dimensional free rotation again. This time, we'll focus on the angular momentum and its z component. So just for review purpose, you have x, y, z Cartesian coordinates. And you have r, theta, phi polar coordinates. R is the vector pointing towards the particle, theta is the angle between r and c, phi is the angle between the xy projection of r and x. So we can express x, y, and z in terms of r, theta, phi here. And for a rigid rotor, r is a constant. Therefore, we replace r with a constant r0. This is the Schrödinger equation in the x, y, z Cartesian coordinates. How can we convert x, y, z to this part to r, theta, and phi? So first, we need to know this r can be expressed as a function of x, y, and z, same as theta, indirectly, because we just defined tangent theta here to be the square root of x squared plus y squared. This is the projection of r on the xy plane, divided by z here, and theta is from 0 to pi, so theta corresponds to the latitude of Earth. And tangent phi equals y over x, and phi is from 0 to 2 pi, so this phi can rotate about the z-axis from 0 to 2 pi, and phi corresponds to the longitude of Earth. And then we can convert this Schrödinger equation in the xyz coordinates to the r, theta, phi coordinates. And where is r? R is r0, and this I equals simply m times r0 squared for a one-particle system. If you have a two-particle system, this I equals mu times r0 squared, where 1 over mu equals 1 over m1 plus 1 over m2. So when you have a linear molecule that consists of 3 atoms, it's a little bit more complicated to get this I, but not so difficult. You just need to find the center of mass first. And then this I is simply the m1 times r1 squared plus m2 times r2 squared plus m3 times r3 squared, where m1, m2, m3 are the mass of the 3 atoms, r1, r2, r3 are the distances of those atoms to the center of mass. By solving this Schrödinger equation, we'll get those eigenfunctions over here. The first one is a constant, and then we have cosine theta, sine theta times e to the plus minus I phi, and a function of cosine theta and sine theta cosine theta times e to the power of plus minus I phi, and over here sine theta squared times e to the power of plus minus 2I phi. What's the physical meaning of this? This really is a spherical function because it does not depend on theta or phi. So it corresponds to the s orbital. And over here, this is actually just z over r. And in this case, when r equals r0, this part is simply z over r0. That's just the 2pz atomic orbital. Over here, you are looking at the linear combination of 2px and 2py. Over here, you are looking at simply the 3D z squared orbital. Over here, you are looking at this linear combination of dyz and dxz. And this one is the linear combination of dxy and dx squared minus y squared. And over here, the shapes of the eigenfunctions. The first S-type eigenfunction, 3 P-type eigenfunctions, 5 D-type eigenfunctions, and 7 F-type eigenfunctions. And also the degeneracy is 1, 3, 5, or 7. Now we'll talk about the angular momentum. So first, angular momentum Lx, Ly, Lz are the 3 components of the three-dimensional angular momentum. They have corresponding operators, and the operator Lx is simply negative IH bar times y times delta over delta z minus z over delta y. So what is this? This is simply y times the pz operator minus z times py operator. And the PZ operator is negative IH bar times delta over delta Z. And the PY operator is simply negative IH bar times delta over delta Y. So similarly, we have this LY operator and LZ operator. What about the three-dimensional angular momentum? This is also a vector that contains three components in x, y, and z direction. Also, we can write them out in this form. Lx as a scalar times the unit vector I in the x direction plus Ly times j plus Lz times k. How about the operators? Similarly, the L operator is equal to the Lx operator in the I direction, Ly operator in the j direction, and Lz operator in the k direction. I'm sorry, I, j, k are the unit vectors in the x, y, and z directions. And then we'll prove that Lx and Ly do not commute. Actually, any two of the three do not commute. So we're just using this as an example. So this is the notation for the commutator, which equals Lx, Ly minus Ly, Lx. We changed the order of the two operations. We apply this commutator to an arbitrary function f, and we get this expression. And then we plug in the expression of Lx, so this one, and the expression of Ly, which is this one. So it looks complicated, but really it's just Lx, Ly here, Ly, Lx here. All right, so we just derive this. This term consists of you have this two multiplication, and then two cross terms. There are a total of 4 terms. And over here again, 2 terms times 2 terms, you get 4 terms. All right, so really you have a total of 8 terms. And then you try to simplify this term, this 4 terms. You get 1, 2, 3, 4, 5. Actually, you get 5 terms. And this 4 terms becomes, again, this 5 terms. And then fortunately, the red term and this red term, they cancel. Look at the negative sign here. So these two cancel. The 2 purple terms cancel. The 2 blue terms cancel. The 2 green terms cancel. So in the end, it's actually pretty simple. It's just IH bar times negative IH bar times this guy. And what about this guy? This guy times negative IH bar is simply the LZ operator. So in the end, the commutator of Lx and Ly is simply IH bar LZ. And it's non-zero. That means we cannot determine Lx and Ly simultaneously and exactly. Similarly, we have Ly LZ commutator to be IH bar times Lx, and the commutator of LZ and Lx to be IH bar times Ly, and that means if you pick any two out of the 3 angular momentum operators in the x, y, and z directions, they do not commute, they cannot be determined simultaneously. So if you know the angular momentum in the z direction, you won't be able to get the angular momentum in the x or y direction. All right, so now let's look at the L squared operator. So if you apply this L squared operator to the wave function, so what is L squared operator? So you have this L operator. L operator is Lx, this guy times the unit vector in the x direction, and then you have this times j, the unit vector in the y direction, and then you have this in the z direction. So how do you get this L squared? L squared operator is simply this guy squared plus this guy squared plus this guy squared. All right. So if we do that and apply this L squared operator to the eigenfunctions, so over here I showed you all the eigenfunctions all the way from here, the s orbital, the p orbitals, the 5d orbitals, those are eigenfunctions. So if you apply the L squared operators to those eigenfunctions, the eigenvalue is very simple. It's simply just L times L plus 1 times h bar squared. And what about the magnitude of this angular momentum? That's just the square root of this. Simply put, it's the square root of L times L plus 1, and then times h bar. What about the z component of the angular momentum? That's very simple. It's just m sub L times h bar, where this m sub L can be negative L plus 1, and so forth until m sub L equals L. And over here you can see the degeneracy is 2L plus 1. Okay, we learned that Lx, Ly, Lz do not commute with each other, but L squared does commute with Lz. So fortunately we can determine this L squared and Lz at the same time. So basically it tells us we can determine the magnitude of the three-dimensional angular momentum and its z component simultaneously. All right, and again, still it's impossible to determine this L squared and Lx or L squared and Ly. All right, I'm now giving you an example. So when L equals 2, all right, so we know the magnitude of the three-dimensional angular momentum is the square root of L times L plus 1, and then times h bar, which is the square root of 6 times h bar. And when L equals 2, m sub L can be negative 2, negative 1, 0, 1, 2. Okay, that's telling you we have a degeneracy of 5, just like the 5 different d orbitals. And this 5 numbers tells us the z component of the three-dimensional angular momentum is m sub L times h, which can be negative 2h bar, negative 1h bar, 0, 1h bar, and 2h bar. So this picture shows you the magnitude of the three-dimensional angular momentum is this, the square root of 6 times h bar. The length of each vector is square root of 6 times h bar. And let's say this is the z direction, and then we can get the z component. The z component of this vector is the distance between here and the z-axis. All right, so that's 2h bar. How about this guy, 1h bar? Remember here, this vector has a z component of 0. This one has a z component of negative h bar. This one has a z component of negative 2 h bar. Again, the z component of these 5 vectors is negative 2 h bar, negative h bar, 0, h bar, or 2 h bar.